the sum of all the neighbors. This is the first thing. Okay, we can, if we do it like this, obvious answer will be xi equal to 1. That's obvious minimum because it will be 0. Everyone belongs to one group. This is not what we want. We want a partition that is balanced. Well, assume that we have number of vertices. So this is formalized like the sum of all elements of our partition is equal to 0. So it means we'll have approximately equal splitting of our graph vertices into two groups. And formally it's written like a scalar product of the vector x times the vector of all ones is equal to 0. And there is also an additional constraint that we want all ones, and we relax it, that the sum of squares of all x is equal to m. Okay, we want to minimize this. We still have integer programming task, plus minus 1. We have orthogonality condition which corresponds to balanced partitioning, and we have this normalization constraint. And you can obviously guess what we are doing now. This is integer programming. Integer programming is a difficult task. So we just relax this minimization problem. But before that, let's rewrite. So the original one was the quadratic form. A quadratic form can be rewritten as a scalar product with a positive definite matrix, x times x, every quadratic form. And this is called graph Laplacian. This is important. So you have graph, you have an adjacency matrix of the graph, and you also have a graph Laplacian. And this is a symmetric matrix, and the diagonal is equal to the number of neighbors of the vertex. And all diagonal elements are equal to -1 if I and j are connected. This is a symmetric matrix, symmetric non-negative matrix. By the way, question, why this matrix is, if we define this matrix like this, why it is all the eigenvalues are non-negative? Well, it's obviously symmetric. Why it is non-negative? Yes, yeah, it's directly right. So that's one of the ways. Another way is to say, if you write down the quadratic form that is related to this matrix, it's exactly this, which is greater or equal than 0. If you have a quadratic form that is greater or equal than 0, it's obviously all the eigenvalues are not negative. It has eigenvalue equal to 0 because if you take the vector, yeah. This can be constructed for any n. So this, balanced partition, of course, if you have plus minus 1, no, why not? If you have 3, okay, so you say if it's 3, it's not possible to assign, I agree. So assume you have even. We will later relax it from discrete optimization to continuous optimization, everything will be fine. So this problem formally has solution with plus minus 1 if n is even. I agree. Okay, thank you for comment. But now we're just looking at this matrix. This matrix is defined from the graph. So this is what we want to know from this, that it has non-negative eigenvalues and at least one eigenvalue equal to 0. One eigenvalue equal to 0, this is the vector of all ones. If you take the vector of all ones, then you just multiply, and in each row you will get 0. So it has one eigenvector corresponding to the eigenvalue 0. The question whether this is a simple eigenvalue or it has multiple eigenvectors correspond to eigenvalue 0, it's a separate question, which we will mention. So, solving integer programming is a difficult task, but what we do, we now relax this. And instead of minimizing over plus minus 1 vectors, we minimize over the whole sphere with the constraint that we are orthogonal to the vector of all ones. And that's how we will define the our solution. And then when we obtain our solution, we will just look at the sign of the entries of the vector x, and that would be our relaxed solution. How this solution is related to the solution of the original integer optimization problem, again, this is a separate question. There are inequalities, but again, for computation, this is a clear element. Yeah, by the way, what's the solution to this optimization problem? So we're given the matrix A. What is the solution of this optimization problem? So if we do not have this constraint, the minimization of this guy, what will give us? Smallest eigenvector. And what is the smallest eigenvector here for this matrix? Smallest eigenvalue. What's the smallest eigenvalue? It's non-negative, but it has 0. So what's the smallest eigenvalue? 0. Right. But eigenvector is also the vector of all ones. So we require that our x is orthogonal to this eigenvector. So we're minimizing over the subspace which is orthogonal to the eigen vector corresponding to the smallest eigenvalue. What we will get instead? We cannot converge to the smallest eigenvalue if we add this orthogonality constraint. It's not the smallest what we will get. Second smallest, right? So this will converge to the second smallest eigenvalue, and this would be a non-trivial vector. This is called Fiedler vector. So the solution of this optimization problem is called a Fiedler vector. It will have real entries, positive and negative, which sum up to 0 due to this constraint, and we will do clustering based on the sign. That's exactly what's written here. This is a Rayleigh quotient. This is also a special case of so-called Courant-Fisher optimization principle. If you want to find the minimal eigenvalue, you minimize the Rayleigh quotient. If you want to find the second eigenvalue, you minimize over the Rayleigh quotient orthogonal to the subspace corresponding to the smallest eigenvector, corresponding to the smallest eigenvalue, and so on. So you have this variational principles for all the eigenvalues. This is called Courant-Fisher variational principle. How to find minimal eigenvalue, this is a separate story. So power method will find the largest one. How to find minimal, you have to do something else. But when we will discuss methods for eigenvalues, iterative methods for eigenvalues, we will mention. And we will just introduce a class of methods for finding minimal eigenvalues. Yeah, so that's sort of example. Yeah, so that's the current graph. And for this graph, these are the two smallest eigenvalues of the Laplacian. Again, well, there is standard in network X, which this is of course not production library, but for visualization it's okay. So we construct Laplacian, we find two smallest eigenvectors using some sparse solver. This is actually sort of cheating. Because, well, I know what is done inside this code. And inside this code, actually, there is a solution of linear systems with sparse matrices. Well, the default version. And we are trying to use this eigenvalues to solve sparse system. So this is sort of cheating, but okay. We are doing it for visualization. Doesn't matter much. We just have the Laplacian. We have the yeah, that's how the Laplacian looks like, and these are the two smallest eigenvalues. One is 0, as expected, and another one is non-zero. Before that, maybe I'll add what happens, what can we say about the graph if it has two smallest eigenvalues equal to 0? When is it so? Not simple eigenvalue, but for example, there is a non-trivial eigenvector corresponding to 0. Yeah, it will have two disconnected components, for example. If it has two zero eigenvalues, it will have two disconnected components. If it has three, it will have three disconnected components, and so on. If you have diagonal matrix, the Laplacian is zero, right? No one is connected to anyone. The degree is zero. Yeah, so this is the, so if you have, for example, a very small number here, this is sort of the graph, there are strongly connected components which are weakly coupled. Okay. So we just compute the eigenvectors, and that's when we take the sign. So I basically assign the plus and minus 1 to different vertices, and this is our splitting. And this splitting, well, is not so trivial, but when we just color the nodes, which give us a very reasonable splitting of the nodes into two groups. So this is much more connected, this is much more connected, and the number of connections is small. So this relaxation to an eigenvalue problem for this small graph is very reasonable. So, yeah, so we can use chi-pi-sparse to find fixed number of eigenvalues, but again, what's going under the hood there, that's a separate story. There is a big solver there which uses many things. But Laplacian plays an important role. Still, people are trying to use, even nowadays it's an interesting story, because well, so clustering is a sort of unsupervised, well, it's one of the main unsupervised learning algorithms, and there are quite a lot that could be done. So, for example, when I'm trying to do some project, because well, really for large-scale problem where the dimensionality of features is large, using such kind of approaches becomes complicated and very expensive. So, of course, if you have images, you can take some pre-trained network, project, and do something like that. And for example, for small problems, when you have, say, 50 dimensionality of the feature vector 50, you can also do clustering using much more advanced relaxation, but the scaling of this algorithm to higher dimensions that is much more complicated. And then you can use the semi-algebra tools with some advanced model order reduction techniques based on Krylov subspace, rational Krylov subspace, and so on, to reduce the dimensionality combined with some other. So that's actually very interesting and not very well developed topic, in fact. So people are doing well deep neural networks and then so on, but for clustering, it's not so wonderful. Okay? So finally, just notation connection to the graph properties. So the second eigenvalue of the Laplacian has a special name. It's also called algebraic connectivity, and that's the claim. That you already guessed. So it's greater than zero if and only if the graph is a connected graph. So if the second eigenvalue is larger, it means the graph is better connected, and so on. And there are also bounds which connects this algebraic or relaxed connectivity to, well, more classical graph measures of connectivity. So this was the class of method that is used, that uses Laplacian of the graph and graph partitioning. The disadvantage is that you have to basically compute these eigenvalues, and this is additional solver and so on. So another big class of approaches, and if you run chi-pi-sparse as per solve, this is what is working. Not this, but the sort of heuristic approaches. So, for example, the simplest idea is that you do elimination, and now let's get back to matrices. We do elimination, and we only eliminate the vertices that have sufficiently small degrees. But again, for it's suboptimal. Even when I say 2D problems, it means the graph has this two-dimensional structure, like a two-dimensional grid. But if you have a medium-sized problem, because you have the overhead is very small. The overhead of the computations is very small, so the total computing time may be much faster. And yes, I have to fix what's written here. And if you have a non-symmetric matrix, well, you have to